Welcome to the first chapter. It is acid, bases and salts. Now we introduced acids and bases in Form 1. We studied the simple properties and their strengths. We compared using the litmus paper and the pH scale. Later on in Form 2 we studied the salts. We looked at various types of salts, the chlorides, the carbonates, hydrogen carbonates, sulfates, sulfides, nitrates and so on. We looked at the methods of preparing these salts. We studied their solubilities as well as the effects of heat on these salts. Now in this chapter, the properties of acids, bases and salts are discussed in detail. In addition, the definitions and strength of these compounds are given based on their properties and the particles they consist of. The effect of solvent in determining the acid base is also explained using relevant examples. Now this topic is very important in terms of application and especially quantitative analysis in cation-anion identification as well as use of solubility curves in salt extraction. So we start with a look at the strength of acids, and to do that we're going to demonstrate two reactions here. Magnesium is reacting with two acids. The first part, magnesium is reacting with hydrochloric acid, and on the second part, magnesium is reacting with ethanoic acid. Now if you look at those two reactions, it's eminent that the reaction between magnesium and hydrochloric acid appears to be more vigorous compared to that between magnesium and ethanoic acid. Now I want to explain that difference between those two acids, or rather those two reactions. Now, one of the things that you and I know is that metals react with dilute acids to produce salt and hydrogen gas. For example, magnesium would react with hydrochloric acid to produce magnesium chloride, which is a salt, and hydrogen gas. The production of hydrogen gas was eminent by production of the bubbles. The reaction for that is indicated there. So on the other hand, magnesium again would react with ethanoic acid at a slow pace to form a salt called magnesium ethanoate, and again hydrogen gas is also liberated according to this equation. Now the hydrogen gas is formed when hydrogen ions present in the solution are displaced by the magnesium. So you see magnesium reacting with hydrogen ions to form magnesium ions and hydrogen gas. On their part, carbonates react with acids to form carbon 4 oxide, water and a salt. For example, sodium carbonate would react with hydrochloric acid to form sodium chloride, carbon 4 oxide and water according to this equation. Equally, the same sodium carbonate would react with ethanoic acid to form a salt called sodium ethanoate. Carbon 4 oxide is liberated and water is also formed, again according to that equation. On the part of the carbonate, the carbon 4 oxide and water are formed when hydrogen ions present in the aqueous solutions of the acid react with the carbonate ion according to this ionic equation. You see, from these experiments it is clear that aqueous solutions of acids contain hydrogen ions. An acid can therefore be defined as a substance which dissociates in water to give hydrogen ions. But there is a difference. There are more hydrogen ions in the aqueous hydrochloric acid than in aqueous ethanoic acid, and this is why hydrochloric acid reacts faster with magnesium and sodium carbonate. Similarly, there are more hydrogen ions in aqueous sulfuric acid than in ethanoic acid. This would explain why aqueous solution of sulfuric acid would react faster than ethanoic acid when they react with metals or even carbonates. So acids such as hydrochloric acids and sulfuric acids are called strong acids. In aqueous solutions, such acids dissociate completely into ions. For example, aqueous hydrochloric acid dissociates completely into hydrogen ions and chloride ions. Now the complete dissociation is indicated by the forward arrow. That arrow indicates that that reaction only proceeds in the forward direction. Now weak acids like ethanoic acid dissociate partially in aqueous solution. So like ethanoic acid would dissociate into ethanoate ions and hydrogen ions. The partial dissociation is indicated by those arrows which indicate the reaction can proceed forward or backward. Other strong acids include sulfuric acid and nitric acid, while ethanoic acid, ethanedioic acid, and methanoic acid are all ranked as weak acids. Other attributes are pH and electrical conductivity. Now, strong acids have lower pH, which means they are more acidic. Why? Because they dissociate completely into ions. They also have a better conductivity compared to weak acids. Again, for the same reason, due to the complete dissociation, they will have very many ions in the solution, and these ions are responsible for conductivity. Now, weak acids have a higher pH, which means they are less acidic. Again, because of the partial dissociation, the conductivity is not as good as that in strong acids. Why? Because there are few ions to conduct electricity in the solution. Now, the lower the pH, the stronger the acid. Acidity is determined by the concentration of hydrogen ions. So when the acid completely dissociates, it means the concentration of hydrogen ions in the solution is very high, and therefore the acidity is also high, which means the pH is very low. Conductivity, on the other hand, is determined by the concentration of ions in the solution. If you recall, in the structure and bonding, we said conductivity is either by free ions or delocalized electrons. So the more the number of ions, the higher the conductivity. Next is bases. Now, when a red litmus paper is placed on pellets of sodium hydroxide, there is no observable change that occurs. However, when the sodium hydroxide pellets are dissolved in water, the resulting solution turns the red litmus paper blue. In solution, sodium hydroxide dissociates into sodium and hydroxide ions. Now, the hydroxide ions are the ones that turn the red litmus paper blue because of their basic properties. When hydrochloric acid is added to the solution of sodium hydroxide, a neutralization reaction takes place. Usually we use a phenolphthalein indicator to show the endpoint, and the endpoint is the point at which the acid is just enough to neutralize the base, which means the solution is neutral. Now, sodium chloride and water are formed according to this equation, and the ionic equation shows that hydroxide ions react with hydrogen ions to form water. The hydroxide ions originate from the base, that is sodium hydroxide, and the hydrogen ions originate from the acid. Now, bases react with acids to form salt and water. Now, from this reaction, a base can be defined as a substance that dissociates in water to produce hydroxide ions. And one more thing, just like in strong acids, strong bases completely dissociate into ions. You've seen sodium hydroxide, which is a strong base, dissociate into sodium and hydroxyl ions. The complete dissociation is indicated by the arrow that shows that that reaction proceeds only in the forward direction. For this reason, strong bases have higher concentration of hydroxyl ions, and therefore they are more basic or more alkaline. The pH is quite high. Again, due to complete dissociation, it also means that the concentration of ions in the solution is very high, and therefore the conductivity is also quite good. Weak bases, on the other hand, only partially dissociate in solution according to that equation for dissociation of ammonium hydroxide. For this reason, their conductivity is not as good as that in strong bases. Why? Due to low concentration of ions in the solution. Their pH is also quite lower compared to that of strong bases, again due to low concentration of hydroxyl ions. Remember, in bases, the alkalinity is determined by the concentration of hydroxyl ions. So in partial dissociation, it means there are less ions in the solution. The next item I promised we'll look at is the effects of solvent on a solute, and I want us to look at what we call polar solvents. Water molecule consists of one oxygen atom and two hydrogen atoms which are covalently bonded. Now, since the oxygen atom has a higher ability to attract bond electrons compared to the hydrogen atom, the bond pair of electrons are closer to the oxygen atom in the water molecule. This results in an even electron charge distribution in the molecule, leading to the oxygen atom developing a partial negative charge, while the hydrogen atom develops a partial positive charge, and that molecule is indicated here. Now, a molecule which behaves as if it is negatively charged in one end and positively charged in the opposite end is said to be polar. In this case, water is a polar solvent. Another polar solvent is hydrogen chloride molecule. Hydrogen chloride molecule is made up of a hydrogen and a chlorine atom which are covalently bonded. Now, the reason why it is polar is because the chlorine has a higher ability to attract bond electrons compared to the hydrogen atom. For this reason, the chlorine end of the molecule develops a partial negative charge, while the hydrogen end develops a partial positive charge. Again, that molecule is indicated there. So when hydrogen chloride is dissolved in water, different water molecules attract both ends of the hydrogen chloride molecule and causes it to dissociate. Now, this implies that the covalent bond is broken in such a way that the shared pair of electrons are left with the chlorine atom, thus creating a negatively charged chloride ion. The hydrogen atom is left with no electrons and thus creating a positively charged hydrogen ion. The equation for that, you can see hydrogen chloride dissolving in water to dissociate into hydrogen ions and chloride ions. Now, the presence of the hydrogen ions in aqueous solution of hydrogen chloride explains why it is acidic and turns a blue litmus paper red, and will also react with magnesium to liberate hydrogen gas. It also reacts with calcium carbonate to liberate carbon 4 oxide gas. Now, the equations for that are shown. You can see the ionic equation there. We have hydrogen ions reacting with magnesium to form magnesium ions and hydrogen gas. Methylbenzene is a non-polar solvent. When hydrogen chloride is dissolved in methylbenzene, its molecules do not dissociate, and therefore no hydrogen ions are present, and hence the solution of hydrogen chloride in methylbenzene does not exhibit acidic properties. It has no effect on litmus paper and does not react with magnesium, neither calcium carbonate. Still on the same, let us look at what happens when ammonia gas is dissolved in both water and methylbenzene. Now, dry ammonia gas has no absolute effect on litmus paper. However, when ammonium gas is dissolved in water, some of the ammonia molecules react with the polar water molecules to form ammonium hydroxide according to this equation. Now, the ammonium hydroxide ionizes to form ammonium ions and hydroxyl ions according to this equation. Now, ammonia gas dissolved on the other hand in methylbenzene without undergoing any change, because methylbenzene is non-polar, and hence there are no hydroxide ions in the solution of ammonia gas in methylbenzene. The solution of ammonia in methylbenzene therefore has no effect on litmus paper. Next, and again a very important section of this chapter, is amphoteric oxides and hydroxides. You recall that acids react with metal oxides to form salt and water only. Now, the reactions are known as neutralization reaction. For example, aluminium oxide, zinc oxide, lead-2 oxide, and calcium oxide all react with acids to form colorless solutions of salts depending on which acid was used. Now, copper-2 and react with the acid to form a blue solution. Now, show the reaction of the respective oxides with nitric acids to form salts and water. Now, in all these reactions, the metal oxides are reacting as bases because they are reacting with an acid. How about if you reacted the same oxides with an alkali, say sodium hydroxide? Now, aluminium oxide, zinc oxide, and lead-2 oxide will again react with sodium hydroxide to form colorless solutions. However, copper-2 oxide and calcium oxide will not react with an alkali. Now, the reactions of aluminium, lead, and zinc oxides with sodium hydroxides are shown in these equations. Now this kind of metal oxides which react with both acids and bases are called amphoteric oxides. Lead hydroxide, zinc hydroxide and aluminum hydroxide are also amphoteric, and they will react with both acids and bases. In these equations you can see them acting as acids reacting with the base, which is sodium hydroxide. Next is salts, and we discussed salt in Form 2. The methods of preparing salts were discussed. We did experiments on the effects of electric current on molten salts and revealed that salts are ionic compounds. For example, sodium chloride consists of charged ions. When an acid reacts with a base to form a salt, the positive ions of the salt are derived from the base, while the negative ions come from the acid. Now, a salt can therefore be defined as an ionic compound formed when a cation derived from a base combines with an anion derived from an acid. Now, a very important area of salts is the precipitation reactions, and a precipitate is an insoluble solid that separates out from a solution during chemical reaction. Now, I want us to look at what happens during precipitation reactions so that you can better understand and conceptualize what happens. But before I even indulge much into that, I want you to understand in precipitation reactions, what usually occurs is what we call ion exchange. We start with two soluble salts and we end up with one soluble and one insoluble salt. The insoluble salt is the one that will precipitate out. Now, for you to be able to better understand this and be able to work out various problems, one of the important things that you have to have at your fingertips is the rules of solubility of salts, so that you can be able to know which salts are soluble and which ones are not soluble. So let us demonstrate this briefly and be able to understand that better. Let us say I have two salts, AB and CD. Now, salts being ionic compounds means that in AB the ions are A is the cation and B is the anion. In salt CD, there are C as the cations and D as the anions. So what happens in precipitation reactions is that when AB is mixed with CD, the ions are exchanged and we form AD and CB. Easy. But careful. You need to be aware that AB and CD must both be soluble, and that either AD or CB is insoluble, but never both. Otherwise, both of them will precipitate and you will not be able to separate. This thus calls for you to know the rules of solubility of salts. Let me remind you a few of them. All salts of sodium, potassium and ammonia are soluble. Again, all nitrates are soluble. All chlorides are soluble except lead 2 chloride and silver chloride. All sulfates are soluble except barium sulfate, and I think I know calcium sulfate is slightly soluble in warm water. All carbonates are insoluble except those of sodium, potassium and ammonia. That comes with little surprise, that rule, because in the first rule we know all salts of sodium, potassium and ammonia are soluble. So in precipitating a salt, you really need to know this. For instance, let me say I want to precipitate barium sulfate. Barium sulfate is an insoluble salt. Now what I need is a salt of barium that is soluble. So let's say I pick barium nitrate. All nitrates are soluble, so let me pick barium nitrate. And again, I will need a soluble sulfate. So let me say I pick sodium sulfate. Again, all salts of sodium are soluble. So sodium sulfate is soluble. I have two soluble salts, barium nitrate and sodium sulfate. So if I mix them, I will have the ion exchange take place and I form barium sulfate and sodium nitrate. Now you realize sodium nitrate remains in solution and barium sulfate precipitates out. Note the insoluble salt has a state symbol of solid. So you need to be careful in choosing the salt so that after the exchange of ions you don't end with two insoluble salts. For example, assuming I had chosen barium chloride and lead 2 sulfate. Yes, both are soluble salts, but look at what happens after the ion exchange. barium sulfate and lead 2 chloride are formed. Now both are insoluble salts and will precipitate. Now you cannot be able to obtain any salt in this case because you cannot separate the two precipitates. Next is complex ions, and this is a very common area in examinations, in chemistry exams. Now I'm going to perform a certain experiment here, and what I'll be doing is that I will add sodium hydroxide solution into solutions containing the ions of magnesium, zinc, aluminium, iron 2, iron 3, copper 2 and lead 2. What I'll be doing is that I will first add small amount of sodium hydroxide to these solutions, and then I will add the excess, and we will see what will be happening at each stage. So let's do this thing. So there we are. The first test tube on the left contains a solution of zinc ions, and then here I have sodium hydrogen. At first I'm going to add little amount and see what happens. You can see the white precipitate there. Let's have a black background. You can see clearly. You can see the gelatinous precipitate there. The next thing I'm going to do is I'm going to add excess amount of sodium hydroxide and see if this precipitate will dissolve. So let us now add excess amount of sodium hydroxide. There we go, and you see indeed the white precipitate redissolves. Next in line, aluminium ions, and we are going to repeat. Here I have sodium hydroxide. First add a few drops, and we see the white gelatinous precipitate is formed there. More sodium hydroxide, more precipitate. Now we are going to add excess and see what happens. And as in the first case, that precipitate redissolves. Copper 2 ions is next. Copper 2 ions blue in color, so we are going to add a few drops of sodium hydroxide. And you see there the gelatinous precipitate, blue in color, forms this time. That's copper hydroxide. And we are now going to add excess, add more sodium hydroxide. The precipitate intensifies, and even with excess, there is no sign that this precipitate is going to dissolve, so the copper hydroxide remains. Next, iron 2 and iron 3. Iron 2 on the left, iron 3 on the right. So on the left, I'm going to add a few drops of the hydroxide, sodium hydroxide. Green precipitate forms there. And on the right, I'm going to add a few. Again, you see red brown precipitate forms. Brown precipitate forms there. So we are again going to add excess in both of them and see if the precipitate will dissolve. So on the left, we add more and more, and the precipitate doesn't appear to be dissolving. Even adding more, dissolving, no. On the right, once again, adding excess, no dissolving, and more and more, and the precipitate persists, no dissolving. So you see from the left, we have zinc ions, formed white precipitate, gelatinous precipitate. Same case with aluminium, second from left, but the zinc and aluminium precipitates dissolved in excess sodium hydroxide. Next we have the copper 2 ions. When we added small amount of sodium hydroxide and even in excess, same case with iron 2 and iron 3, the precipitates never dissolved. The precipitates persisted in copper, iron 2 and iron 3. So closer look, that is copper 2 hydroxide. The precipitate there does not dissolve. Iron 2 ions, that is iron 2 hydroxide. The insoluble hydroxide there from the green precipitate, and then the brown iron 3 hydroxide, never redissolved. After those trials with sodium hydroxide, the next reagent we are going to use is ammonia solution. Now what you've seen there is magnesium ions added, some small amount of ammonia solution, and you can see a white gelatinous precipitate has formed. So just like we did with sodium hydroxide, we first add small amount of ammonia solution. We see what happens and then try and see if we'll have a two-step reaction. How? By adding excess amount of ammonia solution. What we are going to look for is whether that precipitate will dissolve. Adding more ammonia solution, let's see what happens. And we are going to add even more and more ammonia solution and see whether the precipitate dissolves. Well, from my point of view, it doesn't look like there is any hope it's going to dissolve, but we are still going to add more and more and shake. But yes, I'm right, it is not going to dissolve. And looks like this is a one-step reaction. The white precipitate has persisted. It doesn't dissolve even in excess ammonia. Next I have aluminium ions, and I've added small amount of ammonia solution. The white precipitate there has already formed, and what we are going to do now is try and see if we shake whether this precipitate will when we shake, we'll see whether this precipitate will redissolve. So what we are going to do is that we are going to add excess amount of ammonia solution and see whether that precipitate will redissolve. So we add more. And more, and clearly there is no sign that this precipitate is going to dissolve. The precipitate has persisted. Next in line is zinc ions, and I've added small amount of ammonia solution. A gelatinous white precipitate has already formed. Now our idea is to see whether this could be a two-step process, and we are going to add excess amount of ammonia solution and see whether the precipitate will redissolve. Adding more. I can already see signs it's like it's going to dissolve. So let us add more ammonia solution. And the precipitate has started disappearing. We expect a clear solution. We expect a colorless solution there. And that's what we look like we are going to get. Yes, the precipitate has disappeared. It has dissolved in excess ammonia. Next on the line, iron 2 ions. Already added small amount of ammonia solution. The green precipitate has formed. Now again, just as in previous cases, the idea is to see whether this could be a two-step reaction. What we are going to do is find out if this precipitate will dissolve in excess ammonia solution. So we'll keep adding more and more and try and see if it redissolves. So for the second one, nothing changes. The precipitate still persists. I'm going to add even more and see whether it will disappear. Will it? No. Looks like there is no hope that this is going to go away. So it's a one-step reaction. Next on the line, iron 3 ions. Beautiful brown precipitate formed there with small amount of ammonia solution. We add more As we shake and we see the brown precipitate persist, we are still going to add more ammonia solution and see whether that precipitate will redissolve. So more drops, nothing seems to change, the brown color only is. Let's try and see. The brown precipitate still persists and doesn't look like it's going to dissolve. So it's a one-step reaction. The brown precipitate persists. Finally, we have copper. No mistake. Blue color of copper 2 ions. Copper 2 ions in ammonia solution, small amount of ammonia solution. Blue color there appears. We are going to add more ammonia solution and see if that blue color will disappear, or at least if there will be another step. Keep shaking and see. We add more and more ammonia solution and see what happens. Now you might notice the blue color is deepening with time as we add more and more ammonia solution. So let's keep going. The precipitate appears to be dissolving. From far I can see a deep blue solution that is being formed. We can get a better shot of that. Yes, add more. Looks like there is going to be another step. Yes, a deep blue solution is being seen from very far, and yes, the precipitate appears to be dissolving. Add more ammonia, adding more ammonia solution, and the color has really changed from blue to that deep blue, and the precipitate has redissolved. The precipitate has redissolved to form a deep blue solution. You add more ammonia solution, you can see the solution is really, the solution can be seen to be deep blue and there is no precipitate. So it is a two-step reaction. Now, well, so much for that. Now, in this experiment, sodium hydroxide forms insoluble hydroxides with the ions of magnesium, zinc, aluminium, iron 2, iron 3, copper 2, and lead 2. Now, these hydroxides have characteristic appearances which form the basis of their identification. Now, the ionic equations for those reactions are shown here. You realize with magnesium, zinc, aluminium all form white precipitates as well as lead. The hydroxides are white precipitates, they are insoluble. Iron 2 forms a green precipitate. Iron 2 ions are green in color. Iron 3 forms a brown precipitate, while copper forms a blue precipitate. That is when we add little sodium hydroxide. How about when we added excess? When excess sodium hydroxide was added, the hydroxides of zinc, aluminium, and lead reacted with excess sodium hydroxide to form soluble complex ions that were colorless, and that is why the precipitate disappeared according to these equations. Now, potassium hydroxide may be used in place of sodium hydroxide and similar results will be obtained. When ammonia solution was used in place of sodium hydroxide, again insoluble metal hydroxides are formed in the same way. However, the hydroxides of zinc and copper dissolve in excess ammonia solution because of formation of complex ions shown by these equations. The copper forms a deep blue solution. Now, it is observed that it is only zinc hydroxide that dissolves in excess of both sodium hydroxide and ammonia solution. Next, we look at solubility and solubility curves. In Form 2, you studied about the soluble and insoluble salts. Now we also looked at the meaning of saturated solutions, unsaturated solutions, and crystallization, and we also discussed in addition the effect of temperature on solubility. Now in this topic, the solubility of salt will be discussed further. And to begin with, solubility is the maximum amount of a solute required to saturate 100 grams of a solvent at a particular temperature. Now a given mass of a solvent will dissolve a fixed amount of a given solute at a given temperature. Now this fixed amount of solute forms a saturated solution at that particular temperature. And when the temperature of the solution is changed, the amount of solute required to form a saturated solution ultimately changes. Usually solubility is given as mass of a solute dissolved per 100 grams of the solvent. For example, if 20 grams of a salt saturated 25 centimeters cubed of water at 30 degrees Celsius, we can be able to calculate the solubility of this salt at 30 degrees Celsius. How? We get the mass of the solvent, that is water. 25 centimeters cubed of water is equivalent to 25 grams. Why? Because the density of water is 1 gram per centimeter cubed. If you use that to calculate, the mass will be given as mass is equal to density times volume. So 25 centimeters cubed of water is equivalent to 25 grams. So 25 grams of water dissolve 20 grams of the salt. So 100 grams of water will dissolve how much? We calculate that 100 times 20 over 25, which gives us 80 grams. So the solubility of this salt at 30 degrees Celsius is 80 grams per 100 grams of water. Solubility can also be given in terms of moles per liter of the solute at a given temperature. Now, important to know is that the solubility of different salts is affected differently by changes in temperature. Some salt will dissolve extremely well in high temperatures. Some are not affected by temperature, while others are affected to a lesser degree. For example, if you can draw a curve we call solubility curve, we draw solubility against temperature. For instance, you will find potassium nitrate is extremely soluble, is highly soluble, that even at barely 25 degrees Celsius, the solubility is almost infinite, and that salt will dissolve very effectively. On the other hand, if you look at potassium dichlorate, yes, it is affected by temperature, but to a lesser degree as compared to potassium nitrate, and again the effect is uneven. At higher temperatures, the salt appears to be highly soluble. If you look at calcium sulfate, looks like it is hardly affected by temperature. The effect is very small. Same case with sodium chloride. Sodium chloride appears to have constant solubility in temperature, but if you look at calcium sulfate, there appears to be a small effect of temperature rise. Finally, if you look at potassium chloride, again it's affected by temperature, but that effect appears to be almost proportional. As temperature increases, the solubility increases at a constant rate. So those are called solubility curves. The curve of solubility against temperature. Now the next thing I want to look at is crystallization. Now for salt whose solubility increases with temperature increase, it is possible to crystallize the salt. How do we do that? We cool the salt solution from a higher temperature to a lower one, and because the solubility of that salt is determined by temperature, what will happen is that the solubility of that salt will decrease, and you will see crystals of that salt being deposited. For example, let me have a solubility curve for a salt whose solubility increases with temperature. For example, that. Now let me say I cool this solution from 70 degrees Celsius to 40 degrees Celsius. How much salt will crystallize out? Now what you need to do is check the solubility at 70 degrees Celsius. If you do that, I estimate that at 80 grams per 100 grams of water, and then I go and get the solubility at 40. If I do that, is approximately 35 grams. So in between 70 and 40 degrees Celsius, how much salt will crystallize? It is the difference between that solubility. 80 grams minus 35 will have 45. So if I cool this solution from 70 to 40 degrees Celsius, 45 grams of the salt will be deposited. Easy. From that, I go to fractional crystallization, and fractional crystallization is done when we have a solution of two salts. Two salts dissolved in water. We can crystallize one of the salts, or at least a given mass of one salt, without crystallizing the other. Now what happens is that the two salts must be differently soluble in that salt. One of the salts must be highly soluble and the other, well, not very highly soluble. For example, again, let me have two curves. Let me have solubility curves for two salts. Now you realize salt A is highly soluble. At barely 30, that salt is almost infinitely soluble in that solvent. Salt B is well soluble, solubility affected by temperature, but again not as high as A. So to fractionally crystallize one of the salt, let me say B is the one that is possible to crystallize out. What I'll do is that again I will lower the temperature, let's say from 80 degrees Celsius to 50 degrees Celsius. If I lower that temperature from 80 degrees Celsius to, let's say, 40 degrees Celsius, 80 degrees Celsius to 40 degrees Celsius. Now what will happen? Again, let me check the solubility of salt A at 80. How many grams are those? They are 78. But for A, the salt is infinitely soluble there. So again, I go to 40 degrees Celsius. What is the solubility of B? It is 45 grams. And again for A, it's still infinite. So if I cool that temperature from 80 to 40 degrees Celsius, only crystals of B will be deposited. How much of them? 78 minus 45 grams, which gives us 33 grams of B. No salt of A will be deposited, and that is what we call fractional crystallization, and it is done and possible only in salts which one, their solubility is affected by temperature, but one of the salt is highly soluble and the other one is, well, moderately soluble in that solvent, and the effect of temperature on one salt is extremely high and the other one is quite low. The next thing we look at is hardness of water. Now water dissolves many substances as it flows or from its source. Now a lot of dissolved substances accumulate in rivers and lakes. Some of the dissolved substances in the water are harmless and are of biological importance to life, while others cause pollution. Now some of the dissolved substances are calcium hydrogen carbonate and calcium sulfate and also magnesium sulfate. Water containing calcium and magnesium ions does not lather easily with soap. These ions react with soap to form an insoluble substance we call scum. Hard water is water that does not lather readily with soap, while soft water is water that readily lathers with soap. When an aqueous solution of calcium hydrogen carbonate is boiled, it decomposes into calcium carbonate, which precipitates out. The resulting solution forms lather readily with soap. The equation is shown here. Now water hardness, which is removed by boiling, is called temporary hardness. The amount of soap solution used with magnesium sulfate and calcium nitrate does not show any significant change even after boiling. Hardness which cannot be removed by boiling is called permanent hardness. Disadvantage of hard water. Now hard water wastes a lot of soap. There is a lot of soap wastage. Why? Because the soap first precipitates out the calcium and magnesium. Now hard water also stains white clothes. The soap precipitates out calcium ions and magnesium ions as scum, and the scum forms stains on the clothes. There's also deposition of fur, which is calcium carbonate, in kettles, pipes and boilers, and this discolorizes and reduces efficiency of boilers and may cause bursting of hot pipes. But there are methods of removing this hardness, both the temporary and the permanent hardness. One of the methods is boiling, and we've seen that, and this method removes temporary hardness only. distillation, and this method can remove both types of hardness, but it is expensive. We had looked at distillation in Form 1. Addition of sodium carbonate is another method. In this method, the calcium and magnesium ions are precipitated out. This method removes both types of hardness. It is suitable for large-scale use. The other method is addition of calcium hydroxide, and in this process, a known amount of calcium hydroxide is added to water containing calcium hydrogen carbonate. Calcium carbonate is precipitated out according to this equation. Now you need to be careful because addition of excess calcium hydroxide causes the water to be hard. Next is addition of ammonia solution, and aqueous ammonia is added to water containing calcium hydrogen carbonate, which precipitates out the calcium ions according to this equation, and this method can remove temporary hardness only. Finally, we have what we call ion exchange. Now this is a rather complicated method, and in this process hard water is passed through a column filled with some complex sodium compounds, which can be represented by the formula sodium A, where A is a complex. When sodium A reacts with calcium ion, there is ion exchange that we have seen to form calcium A plus sodium ions. Now the calcium ions and magnesium ions are precipitated out as calcium A and magnesium A, where A we've said is a complex. However, the column gradually becomes converted to calcium and magnesium complex, and it loses its ability to remove the calcium and magnesium ions. But this can be recovered by washing it with a concentrated solution of sodium chloride, we call it brine, to form calcium chloride and magnesium chloride, which is washed away, and this way the column is recharged or regenerated. The ion exchange method involves removal of both types of hardness. The equation for regeneration of the column are shown here. Finally, we look at the advantages of hard water. Hard water is not necessarily bad. Why? Because first, it provides calcium, which is essential for strengthening of bones. Hard water also does not dissolve lead from lead pipes because a layer of carbonate is formed as a lining. Therefore, there is no contact between water and lead. Lead is a very poisonous element. It causes a lot of abdominal pain. With that, we come to the end of the first chapter on acids, bases, and salts. So let's take a quick look at the summary of what we learned. And we said an acid yields hydrogen ions in aqueous solution. And one of the definitions of an acid is that it is a proton donor. A base, on the other hand, may be defined as a substance that accepts protons from acids, and an aqueous solution of a base contains more hydroxyl ions than hydrogen ions. A strong acid dissociates completely and yields many hydrogen ions in the aqueous solution. A weak acid, on the other hand, like ethanoic acid, dissociates partially and yields few hydrogen ions in aqueous solution. Some bases dissolve in water to form hydroxide solutions that we call alkalis. An alkali is a soluble base. A strong base dissociates completely in aqueous solution, yielding many hydroxide ions, while weak bases form few hydroxide ions. An example of a strong base is sodium hydroxide. Ammonia hydroxide is a weak base. Strong bases have higher pH, while the weak ones have lower pH. On the other hand, strong acids have lower pH, while weak acids have higher pH. An amphoteric oxide exhibits both acidic and basic properties. Why? Because it can react with both acids and bases. When it reacts with an acid, it acts as a base, and vice versa. We then came and said an acid is a compound which consists of a metal or ammonium ion and an acid radical, for example sodium chloride. The solubility of a salt is the maximum mass of the salt that will dissolve in 100 grams of solvent, usually water, at a given temperature. Very important temperature there. And finally, on hardness of water, we've seen calcium ions and magnesium ions cause hardness in water. The process by which hardness is removed from water is called water softening.
The battery, of course, is now 200 years old and was discovered, it is said, by a fellow by the name of Aloisio Galvani, an Italian. Galvani was in fact lecturing to some of his pupils. He was a lecturer in medicine. Mrs. Galvani was standing in the one end of the room and she was preparing the evening meal because this was done at his home. And Mrs. Galvani was busy attentively listening to her husband, but also skinning the frog's legs. She noticed that when she touched the frog's legs, a twitch occurred. She called her husband over and said, "Have a look at this interesting phenomenon." And Aloisio Galvani came along, looked at the frog's leg, saw the twitch and said, "Wife, what a magnificent discovery I've made." Luigi Galvani wrote a letter to his friend Alessandro Volta. Volta was not a physician. He was what we would today call a physicist, or in those days they were known as natural philosophers. And what Volta did was decided to set up the experiment as Galvani had done, and realized very quickly that what had been discovered was not the essence of life, but some form of energy. And of course, this was electrical energy. These two Italians, they came along and they found that by the use of certain dissimilar metals and chemicals, you could generate electrical power on demand, at will. This opened up a whole new vista for research within the field of technology and science.